Okay, so let's kind of go over some broad ideas, and hopefully no one has a stroke, okay, which would be bad. All right, so here's the two broad ideas that you have to get. That's the difference between a strong acid and a weak acid, okay? So with you have a strong acid like hydrofluoric acid, which, by the way, your first quiz is tomorrow, okay? It's not going to be anything like complex. But speaking of strong acids, you're going to need to know 4 of them, 4 of the 7. You're going to need to know the names and the formulas. I don't care which the 4, you're just going to need to know 4 of them, okay? Sulfuric, nitric, hydrofluoric, whatever, okay? And it's kind of, a lot of it's kind of going to be on that review that I just gave back, okay? So hey, here's write the chemical formula. Oh, find the percent composition. Here's some molarity problems. There's going to be a simple Ka problem, okay, to work. Nothing horribly complex. So here's the main thing that I want you to get at this point. If you take a strong acid, like let's say for example hydrofluoric acid, and you put that in water, this is like chemistry timber, okay? Hydrofluoric acid likes water. It's going to sweep right, okay? Because hydrofluoric acid likes water more than it likes itself. So you're going to get a lot of hydronium ions and some chloride ions. So if this starts off at 0.1 molar, 0, 0, all of this is going to ionize. That's what you're going to add over here. So the main thing being is that this hydronium ion concentration is the same as the concentration of the acid. Now, here's where this plays out with Ka values, okay? So if you look at Ka values and how they're calculated, it's the hydronium ion concentration times the anion concentration divided by the concentration of the acid at equilibrium. Okay, I emphasize again, at equilibrium. So at equilibrium, the initial concentration of this acid is basically 0. Okay, so what do you get if you divide by 0? Mathematically, what do you get? Undefined, right? So this is why when you look down the chart, you will never find a Ka value of a strong acid, because it's either really big, or it's just undefined, okay? So don't ask me on a test, go, Mr. Burkamp, I can't find the Ka value of hydrofluoric acid, okay? You're never going to find the Ka values of strong acids. They don't exist, because at equilibrium, you're basically dividing by 0. So therefore, the Ka values become undefined, or they're really big numbers. Now, if you look down that chart, the index in the back of your book, you're going to find a whole bunch of Ka values. And if you notice on those Ka values, they're really small numbers, so 10 to the negative 5th, 10 to the negative 12th, something like that, okay? So if you look at how you calculate Ka values, the only way you can get a small Ka value is if these numbers on top are very small. So that's one of the things that you need to look at. If you're comparing 2 Ka values and you're trying to figure out which one is the weaker acid, mathematically, let's say that you're going to get 10 to the negative 12th, okay? 10 to the negative 12th is a pretty small Ka value. What that means is that these numbers up on top are really small numbers, which means that it doesn't ionize much. So on a weak acid, just some generic weak acid plus water, you're going to get the hydronium ions and the anions. Now, over here, this is also going to start at 0.1, 0, 0, minus x, plus x, plus x. So unless this is a relatively big value, okay, that's what's called the 5% rule. So unless I pretty much tell you, hey, you need to worry about this, when you subtract this out as an X, it's not going to change this number appreciably. It's like taking a spoonful of water out of the ocean. Yeah, technically you took a spoonful of water out of the ocean, but it's not going to change anything, okay? So, when you look at how you calculate Ka values here, so if you know what that Ka value is, and you're trying to find these numbers, oh, this is going to be X, this is going to be X, this is going to be 0.100 minus X. And again, unless I tell you to worry, and I did on some of these assignments, on some of the problems out of the book, I told you, hey, worry about this X because it's significant. But unless I don't tell you about it, this concentration here is just going to be 0.1. Now here's the difference. This is why you have Ka values of weak acids. Because for weak acids, you're dividing by 0.1, and these numbers up here are pretty small. So this is why mathematically you have Ka values for weak acids, but you don't have Ka values for strong acids. And the smaller these numbers are, mathematically, the smaller the Ka value is. Okay? So what that tells you is the value of that Ka gives you an indicator of the strength of the bond. So here's the dichotomy, is that the weaker the acid is, meaning that it has a smaller and smaller Ka value, the stronger the bond is between the acid, the anion, and that hydronium ion. So if you go to the prom, and you know, this is my high school sweetheart, I have found the love of my life. God bless you, I'm happy for you, okay? That means that this is a very, 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 very strong bond. And you're only going to ionize long enough to go, hi, how you doing? Okay, then you're going to go back to your date. Okay, you are basically not going to ionize at all, okay? Not at all. So if it's a weak acid, you have a strong bond, okay? Now, if it's a strong acid, meaning that you're going to sweep right on chemistry tinder, okay, that means that it's an extremely weak bond. So that's the dichotomy. A strong acid has a weak bond to its anion, and equilibrium sweeps to the right. If it's a weak acid, it has a really strong bond, and equilibrium lies to the left. So, strong acid, it's tender, you sweep right. Weak acid, you sweep left, and you stay in the molecular form. Okay? So that's one of the main things that you have to get straight right from the get-go, is that fundamental difference. So if on the test tomorrow I ask you, hey, if it's a strong acid, which side does equilibrium lie? Think of tender. Oh, we're going to sweep right. If it's a weak acid, you sweep left, and this is how it's going to exist most of the form. Okay? So, weaks, sweep left, strongs, sweep right. Got that idea? So, when you get to the question on question number 12. Okay, so let's talk about question number 12. So, and this is dealing with sulfuric acid, so H2SO4. So sulfuric, you have different types of acids. If you have HCl, this is what's known as a monoprotic acid, because it only has one hydrogen atom. Diprotic acids, oddly enough, have two. Triprotic acids, like phosphoric acid, H3PO4, are known as, you have mono, di, and then you have tri, okay? These are pretty rare. So even if you look at sulfuric acid, the diprotic acid, so here's what happens. H2SO4 itself is a strong acid, which means that this easily ionizes into H and HSO4 minus. So imagine this. here are your parents, right? And a parental unit, whatever. And they have two twins, Timmy and Tommy, right? Timmy is annoying, okay? We're going to do a lot of weird things to Timmy. So basically, you go to the zoo and Timmy wanders off, okay? And the parents are cool with that because Timmy's annoying, okay? So Timmy goes and he bonds off with some other people and the parents are cool with this, okay? So this happens very, very easily. So this is why there's no Ka value for the first ionization of the hydronium ions. This is what makes it a strong acid. Now, at this point, they've lost Timmy, but they still have Tommy, okay? So now Tommy goes near the lion cage. They kind of like Tommy. They already lost Timmy. It's like, okay, this is going to be awkward if we lose both kids at the zoo. It's like, well, what happened to your kids? I don't know. We were at the lion cage. Bad things happen. Okay, I don't know. So mathematically, when you do that second ionization of HSO4 1-, and that's going to turn into another hydrogen and SO4 2-. This one, you'll notice on that second ionization, there is actually a Ka value. So Ka1, when you lose the first hydrogen, that's undefined. There is no Ka value because, again, there's basically none of this left, okay? It turns into this, you sweep right. But now that they've lost one, they're kind of attached to the second one. Not enough, not a strong attraction, but stronger, okay? So what happens here, now you can calculate a Ka value. So let's say this is 0.10000 minus x plus x, okay? So now if you look at this hydronium ion concentration times SO4 2- divided by HSO4 1-, okay? Now, this is a number that we can actually calculate. And here's the reason why. Yes, this thing is going to ionize, okay? But again, now it's going to act like a weak acid. So H2SO4 is a strong acid because it lies over here. HSO4 in that second ionization is classified as a weak acid because now it's lost Timmy, kind of holds on to Tommy, okay? Now, if you go down and you find nitric acid, okay? Nitric acid is a triprotic acid. It's because there's 3 hydrogens. So what happens with nitric acid, H3PO4, now you have triplets, okay? So if you look at the Ka values, if you go down to nitric acid and go across, you'll notice that the Ka values are getting progressively smaller because it gives off the first hydrogen. Okay, now it's down to 2. Then it's tougher to give off that second one. Okay, you get a smaller Ka value. Now if you go down to try and get rid of that third one, that's a really small value. So this is why when you look at nitric acid, there's 3 different Ka values. And the Ka values are getting smaller and smaller and smaller because it's harder and harder and harder to get rid of those kids. The first one, Timmy, hey, who cares? The other 2, they kind of like to get rid of the second one, then they're really holding on to the third one. Okay? So what I'm looking for in your answer on number 12, so let me explain how I want this answer laid out. I say, explain why there is no Ka1 value, but there is a numeric value for K2 in terms of ionization and the resulting mathematical relationship involved. So what word do you think you should have in your answer to number 12? What's the one word you really think you should have? Starts with the letter I, rhymes with nization. Ionization. So if you don't have the word ionization in your answer to number 12, hey, you did something wrong. And if you don't have it, just don't write the word ionization at the end and go, oh, there you go. No. So here's what you should say. Something like this. The initial sulfuric acid ionizes completely, and therefore there is no Ka value because you're dividing by 0. The second one doesn't ionize as much, and mathematically we can calculate the Ka value because there's some HSO4 that still remains. Okay? So that's how you want to approach the question like that. So when I specifically tell you, hey, here's how you want to answer it, and I say, hey, explain in terms of ionization, guess what? That's a word that you probably want to use. I'm just throwing that out there. A bit of a, color me radical, but that's something that I think you should probably talk about. Okay, now, let's talk about question 15. Okay, that last one on the yellow sheet. So here's what you should see, is that when you go on number 15A, and work your way down to B and C. Your first ionization on A should be less than 1%. Okay? You got to set up your chart. Rice chart, HA yields into hydrogen plus your anion. Okay? So you're going to use Ka equals x squared over HA. And then you're going to divide that. On B, that percentage should be around 2%. And on C, that percentage should be around 6%. Okay, so that should be your percentages that you get on A, B, and C. And what you should see is that your pHs are getting higher. Okay, so your first pH should be around 2.5. That last pH should be around 3.5. Okay? So here's what's happening. Basically, there's a couple of ways you can think about this. If you notice on 15, the molarity is decreasing. We're making it weaker and weaker and weaker and weaker and weaker. Okay? So what that means, there's two ways you can approach this. One option is that basically this stuff is becoming more and more like water because it's becoming more and more and more dilute. So, because if you have pure water, the pH is 7. So as this solution becomes more and more and more dilute, you're basically making it more and more like water. Oh, the pH is going to, if it's pure water, it'd be something around 7. Okay? So conceptually, you look at that, oh, okay, you're right, it's more dilute. Yeah, it's getting close to water, pH should go up. The other thing that you'll see is that the more dilute it is, okay, mathematically, you're going to get a bigger value for the concentration of your anions at equilibrium. Because the more dilute it is, it's like it's easier for it to ionize because it's less crowded. And if it's less crowded, it's easier to transfer those over. Now, here's the other reality, okay, that I want you to get out of number 15. So you have Ka equaling your hydronium ion times your anion divided by HA. Okay? And that Ka is 1.8 times 10 to the negative fifth. Okay? Now, here's what I want. This is the kind of the big idea. Mother Nature is going to do whatever Mother Nature has to do to get to that equilibrium, because that's when Mother Nature is most stable. Mother Nature is this hookah-smoking, gray-haired, tie-dyeing, wearing old lady who's sitting around going, stop. Okay? Mother Nature, she gets real cranky when she's out of equilibrium. And she's going to do whatever she can to maintain equilibrium. Okay? So mathematically, Mother Nature is going to do whatever Mother Nature has to do to get this equal to 1.8 times 10 to the negative fifth. Okay, because that's when Mother Nature is most stable in this situation. So mathematically, look what happens. When you go down on 15, you're going from 0.5 to 0.05 to 0.005. You're making this number here smaller and smaller and smaller. You're going to 0.5 to 0.05 to 0.005. These numbers that you're dividing by are getting smaller and smaller and smaller. But Mother Nature still wants this same Ka value of 1.8 times 10 to the negative fifth. Okay? This is your overriding theme. Oh, Mother Nature's going, I don't care what you all do over here. I honestly don't care. This is Mother Nature's attitude. I don't care what you all do, but I want this number. And I'm going to do whatever I have to do to get this number. So as this number is becoming smaller, these numbers up here also have to become smaller so that you get the same value of 1.8 times 10 to the negative fifth. Because if you're dividing by a smaller and smaller and smaller number, you have to have smaller and smaller numbers up here to produce the same Ka value. So that's the overriding theme that I want you to get. I said, wow, there's a rationale for this. Mother Nature is chilled out. I want this number. You make this number smaller, fantastic. I'm going to drop these numbers and make them smaller as well. Okay? So if you view it through that prism, and if you're really going to understand this, just don't get wrapped up in the numbers. Look at the numbers. Go, wow, what do these numbers mean? Why are these numbers happening like they are? And that's what you need to be able to do. You need to step back and go, hey, this isn't just about writing answers on a paper. What's the trend? What do these numbers actually mean? Okay? And that's how you're really going to understand what happens with this whole concept of equilibrium. Now, let's talk about some of these out of the book. That one on question 53. So on 53, make sure that you have 4 distinct answers. Okay? So on 53, I want 4 distinct answers. I want an anion concentration. I want a hydronium ion concentration. I want the concentration of the acid. And I want the Ka value. Okay, so you should have 4 distinct answers on 53. And do not write down numbers and think, oh, Bergkamp will know what these numbers are. No, I'm not. If I was psychic, I would have won the lottery by now. Okay? Don't just write down numbers and think, I'm going to know what they mean. Okay? So what you should see on 53, you should, on 53, because the 53, if your anion concentration is wrong, everything else is going to be wrong. So your anion concentration on 53 should be 0.011. Okay? Now, in this situation, here's what's kind of cool. You're reacting this with water, you're getting your anion. We'll do the shortcut version. So, if you set up a rice chart, and when in doubt, you set up a rice chart. This is 0.100, this is 0, this is 0. Now, you're told that it's going to ionize 11%. Yes? Yeah. So, when that ionization is 5% or above, that means when you subtract it, it's significant. It's going to impact the value of equilibrium. So here's your rice chart, okay? So you're told that it's going to ionize 11%. So if you take 11% of 0.100, that gives you your equilibrium numbers. So if you take 11% of 0.1, okay, 0.11 times 0.01, you get 0.011. And because it ionizes in a 1-to-1 ratio, these two numbers are the same. Okay? These are both 0.011. Now, since this is so big, relative to this number, okay, relative to this number, this is a big value. So when I subtract it, I actually have to take that into consideration. So I'm going to go minus 0.011, oh, next one, plus 0.011, plus 0.011. So that's going to be 0.089. So at equilibrium, because this is so big, okay, relative to this number, I have to take that into consideration. So at equilibrium, this is going to be 0.089, 0.011, 0.011. So when you calculate Ka, this is what you have to use for that denominator, okay? Don't use 0.1. You have to use what it is at equilibrium. And most of the time we don't worry about it, but since this is such a big value, it alters this. So one of the things I'm going to look for, when you say, hey, Mr. Burkamp, here's how I calculated Ka. That's 0.011, and you can just square that. And make sure that you're dividing by 0.089, okay? Because it's so big that you have to take that into consideration, okay? Now, when you get to 56, okay, you're given the pH. You can find your anion concentration just by taking 10 to the negative 3.65, okay? So the tricky part on 56 is this. Ka is going to be your hydronium ion concentration times your anion concentration divided by X minus okay. So in 56, this is how this would play out. I would give you a sample of this solution and a pH probe. And you would take the pH probe and you would measure that. And you're going to get, in this case, whatever that was, 3.65. And you're going to try and figure out what's the original concentration of the acid. So here's the only way you can do this. If you set up a rice chart. So if you set up this rice chart, you take 10 to the negative 3.65, you get this 2.39 times 10 to the negative 4. Do not round this number too much, okay? When you're doing these sub-calculations, keep more digits and then round when you get to the end. So, you know what the Ka value is, okay? You know this number. You know what your hydronium and your anion concentration is because you know what the pH is. So this ionizes in a 1-to-1 ratio. So as soon as you know your hydronium ion concentration, you also know what the anion concentration is. So when you set up that rice chart, okay, and when in doubt, set up a rice chart. So this is your unknown, that 0, 0, minus 2.239 times 10 to the negative 4th, plus that. So at equilibrium, that's X minus 2.239 times 10 to the negative 4th, and then that's that same number over here. And literally, if you look at my answer key, every one of these problems I've set up a rice chart. And I've been doing these problems longer than you all have been on this earth. And there's a reason I do the rice charts, is because it works. It forces you to think through it. Okay, so on 52, because if this first number is wrong, everything, excuse me, on 62. On 62, the first thing that you need to figure out is the molarity of the acid. So in 62, that initial molarity should be 0.0222 mole. So when you take those 1,000 milligrams and change that into moles and then divide that by the volume, this should be your molarity. Because if that's wrong, the rest of the problem is going to be a train wreck. Okay? So again, set up this rice chart. And here's the whole key to that rice chart. This is at equilibrium. That's going to be 0.022 minus X. This is going to be X. This is going to be X. So you have your Ka equaling X squared divided by 0.022 minus X. So then it turns into a quadratic. So, quick refresher, your quadratic. What's the quadratic formula? Negative b plus or minus
the square root of b squared
minus
4ac
all over
2a.
2a. Okay? Now, here's what you have to understand. When you get X, that's your hydronium ion concentration. Take the negative log of that, there's your pH. So if all goes well on 62, when you get X, that should be something around 3 times 10 to the minus third. Okay? So when you solve that quadratic, the X that you're going to get should be something around 3 times 10 to the negative third. That's an ish, okay? But it's going to be somewhere in that ballpark. Okay? All right. Anything you specifically else you want me to specifically go over? If you have any hesitation on anything that you've done, ask me and I will tell you. Mainly because it's easier for me to grade papers that are right than papers that are wrong.
Can we go over 14 real quick?
Anything but that one. I won't go over. Yes. Okay. So, use the Ka values, okay? Determine the concentration of the hydronium ions, right? Okay. So on 14, here's how you want to start. Look up the Ka value, right? And you're going to get 3 times 10 to the negative 8. So you have Hakel, which is the actual formula, turning into hydronium ions and OCLs. So this is 1.5, 0, 0, minus x plus x plus x. 1.5 minus x, x, x. Old hat. Okay? Old hat. And tomorrow, if you hand in your quiz and you haven't done something like this, you've done something horribly wrong. Okay? So this is 1.5 molar. We're not going to have to worry about subtracting the x because it's such a small value. So then, your Ka is going to equal x squared divided by 1.5. So you can find your hydronium ion concentration, which should be something around 2 times 10 to the negative 4th. Okay? So this x should be about 2 times 10 to the negative 4th moles per liter. So then your hydroxide ion concentration, oh, okay, well, remember your hydronium ion concentration times your hydroxide ion concentration equals 1.0 times 10 to the negative 14th. So once you know this, put that in there, divide that into 1 times 10 to the negative 14th, there's your hydroxide ion concentration. Then your OCl concentration is just going to be the same as your hydronium ion concentration because that ionizes in a 1-to-1 ratio. Your HCl concentration is just going to be 1.5 because that's not going to change. So if all goes well on 14, when you find that pH at the end, that should make a fairly decent GPA. Okay? Not stellar, but not bad. Okay? Especially if it's just a 4.0 GPA. Non-weighted GPA, your answer to 14E would be pretty decent. Okay? Not phenomenal, but not bad. Okay? Are we good, Morgan?
Yep.
That answer that one? Okay. Anyway. Anything else? Yes, Al.
So I forgot to do rice charts on most of them. Should
Yes.
So did I.
So, should we rewrite them?
Get annihilated. I did. Hey, no strokes. You said no strokes.
What if we
Don't
all
worry,
agree to do it
I
from
did
now on?
rice charts.
If you didn't do them, don't go back and redo them. But from now on, do them. Now, so this is just an old sage, okay? An old soul. And this is just true of anything. When you have a teacher that's up here going, hey, this is how you should do them because it works, guess what? That's probably how you should do them. Because here's the deal. Here's what I have to undo. Here's my challenge, Al. Is that for the past 12 years of your education, you've only focused on writing down the answer, okay? Because that's what most teachers grade, is just that answer, okay? And they didn't care about the process. I care much more about the process than I do about the answer. So if I can't follow the process, then I really don't care about the answer, okay? So that's why I want you to get in the habit of doing these rice charts. And I'm not doing it to be a jerk. I do it because you're really going to understand the process if you do a rice chart, because otherwise you're just getting an answer and then you don't know what it means. So you don't have to go back and redo them, but from now on, do rice charts. Okay? Are we good? Anything else? Going once? Yes.
It's on the old worksheet. It's the electron configuration one. It's like how many single and pair valence electrons. Like carbon and oxygen are the same, right?
Here's the reason why. So you look at carbon. Carbon is 1s2, 2s2, 2p2, right? Oxygen is 1s2, 2s2, 2p4. Okay? So the whole key is that p sublevel has 3 orbitals. So remember, you put 1 electron in each orbital. So here are these p sublevels, right? So we're going to have an electron here, an electron here. Okay? Now with oxygen, 1, 2, 3. So there's 4 electrons. So I'm going to put 1 here, 1 here, 1 here, and then I'm going to double that up. So yes, they both have 2, but the structure is completely different in terms of the number of electrons. So yes, they both have 2 orbitals that have 1 electrons, but the whole structure of the outer shell is completely different. So this is why oxygen has an oxidation number of 2 minus, because it's going to gain 2 electrons. Carbon is going to tend to form covalent bonds because it's going to share those 4 outside electrons. So that answer is the same for both of them, but the outside structure is completely different. Okay? All right. Anything else? Going once? Going twice? So, and again, when you're, just make sure that you have left lots of room in between pages for answers, because that makes it easy for me to grade. I hate stuff that all just gets jumbled together because that drives me crazy. All right, Adam, stop that for a second. Or Morgan. Okay. So far we've talked about weak acids. So now we need to talk about weak bases. So it's a similar type idea, but it's not, if that makes complete sense. So here's the deal. So the weak acids, it ionizes into hydroniums and anions. Here's how you calculate Ka. That should be old school. Okay? Now here's what's important. A lot of times when we do that with weak acids, we leave out the water because we're kind of lazy, and it's like, oh, do we really have to write the water? But here's what's going to be important. So technically, when you have that weak acid and the water is here, and you get hydronium ions and the anions. So technically what's happening here is the water is actually acting as a base, okay? Because the water basically comes up to the acid and goes, hey, so acid says, hey, I got this hydronium ion, really not that attached to it. Water says, hey, I'll take it. Oh, chill out, okay? So that proton loses its bond with the anion, and you get hydronium ions and the anion, right? And if it's a strong acid, you sweep right, and it lays, when you end up over here. If it's weak acid, it exists mostly as a molecular form. So most of the time we don't write water, it's just implied that it's there. So this is the more technically correct version of it. Okay? But a lot of times you just don't worry about it. And here's how you calculate Ka. And again, when you're talking about K, what's the only time you use uppercase K? When the system is in equilibrium. Okay? And typically your Ka values are pretty small numbers, 10 to the negative fifth, 10 to the negative 12, something like that. Okay? Now, when you talk about weak bases, okay? So weak bases, here's the difference. You have to write in the water. So when you're talking about the ionization of and the reaction with water, you have to include the water, okay? It has to be there. Because here's what happens. This base comes along and it comes up to the water and says, "Sup, I need one of your protons." So what happens is that this base takes a proton from the water. And then it looks like it's an acid because it's Hb+. So this is the conjugate acid. So to form this conjugate acid, you take a proton, you add it to it, and then what's left over is hydroxides. So here's the difference. Okay, here's the most important difference. A weak acid is going to generate hydronium ions, which is going to make the solution more acidic, which is going to make the pH go down. A base is going to form hydroxide ions, which is going to make the solution more basic, which is going to make the pH go up. Okay? So this drives the pH down. This drives the pH up. Okay? That's one of the most important things. So the other thing that's going to happen when you set up like a rice chart, when you solve for X here, you're finding the hydroxide ion concentration. When you find the X here, you're finding the anion concentration. Okay? And the hydrogen as well. So this X gives you your hydronium ion concentration. When you solve for X here, you get the hydroxide ion concentration. Okay? Now, I'm going to go through kind of this big proof. Don't write it down, okay? Just pay attention to the conceptual part of it. So I'm never going to expect you to work out what I'm about to do. I'm going to expect you to understand the concept of it. If you want to, you can write it down, but I'm not going to expect you to know it. So here's the deal. So let's say that we take like some ammonium nitrate, and we're going to dissolve that in water. So we're going to have NH4. I'm going to put that in water. And like I said, don't worry about writing all this down. This can take me a while to write out. Okay. So, and you're actually going to do both of these reactions in the lab. So in this situation, you're going to add ammonium ions, okay? You can get ammonium ions from, like, let's say, for example, what you're going to do in the lab, you're going to take ammonium nitrate, okay? Ammonium nitrate makes the fertilizer. It's an NH4 and an NO3, and it's very soluble because it's nitrate, and all ammoniums are soluble as well. So what would happen is that you would take this as ammonium nitrate and you dissolve it in water. So you've got this free-floating cation in the water. It comes up to the water says, yo, sup? I'll take one of those protons off your hands. So it's going to take one of these protons, and you're going to be left with an increasing concentration of hydronium ions. So, and ammonia, okay? So, because we're producing hydronium ions, what you'll see when you do this particular reaction, you'll see the pH go down because you're producing H3O. You're increasing the concentration of your hydronium ions, and you'll see a slight drop in the pH, okay? So if you were to write the value for the Ka here, this would be your hydronium ion concentration times the concentration of your NH3 divided by the concentration of your NH4. Okay, just mathematically, this is how you would calculate it. Now, with this one, if you do ammonia, this one is a demo that I will do because ammonia itself is horribly, horribly potent, and it will like literally cause damage to your lungs if you inhale it. So I'll do this as a demo in the fume hood, okay, later on. So you take ammonia, and it's a gas, and you put it in with water. So what would happen is that we're going to take a beaker, and we're going to bubble ammonia into, we're going to generate ammonia, and we're going to bubble it into the water. And what you'll see is ammonia is very soluble because water and ammonia have very similar type molecular structures. So what's going to happen is that the ammonia is going to go up to the water and go, yo, sup? It's going to take a proton away from the water. And you're going to generate hydroxide ions. So what's going to happen here is that this one is going to make the solution more basic. So this reaction makes the solution acidic. This reaction makes the solution basic because this is generating hydroxide ions and this is generating hydronium ions. Okay? So this drives the pH down. This drives the pH up. So if you were to write the Kb expression, you would take NH4 times OH divided by this. Now here's one of the things you see again and again and again and again and again. Anytime you're doing this type of reaction, it's always products over reactants, okay? So this is one of the absolute golden rules of chemistry. Anytime you're writing any kind of expression, it's always products over reactants, okay? Always. No exceptions whatsoever. It's always products over reactants. So, what I want to do is I'm going to multiply Ka times Kb, right? So I'm going to take that Ka expression, which is my hydrogen times my NH3 divided by my NH4. And then I want to multiply that by this concentration, or that expression, which is going to be NH4 times OH divided by NH3. Now, look what happens. So I've got NH3 down here and NH3 up there. Okay, those cancel out. I've got NH4 here and NH4 here. Those cancel out. So when you multiply Ka times Kb, you're left with your hydronium ion concentration times your hydroxide ion concentration, which also, oddly enough, equals 1.0 times 10 to the negative 14. Okay? So, if you know what the Ka value is, you can automatically figure out what the Kb value is. Because just like your concentrations multiplied together, equal the auto ionization constant of water. Again, do not tell me, oh, 1.0 times 10 to the negative 14, that's water. No, I will flip out, okay? This is not water. It's the auto ionization constant for water, but this is not water. So, here's the ramifications. Oh, right. If you look at this, as your hydronium ion concentration goes up, oh, your hydroxide ion concentration is going to go down. As your Ka value goes up, guess what? Your Kb value is going to become smaller. So here's the deal. So let's look at this situation. So hydrofluoric acid, so we're going to deal with hydrofluoric acid. So hydrofluoric acid, if you look in your book, has a Ka value of 6.8 times 10 to the negative 4th. Now, the cool thing about hydrofluoric acid, fluorine is one of the halogens, fluorine, chlorine, bromine, iodine. Hydrofluoric acid is the only acid that has a halogen as the anion that is a weak acid. All the other ones, chlorine, bromine, iodine, all the other ones are strong acid. So fluorine is the odd one out. It's the only acid that has a halogen as the anion that's a weak acid. And the reason being is that fluorine has a pretty strong attraction to the hydrogen. And the reason being is that if you look at the structure of fluorine, okay, how many valence electrons does fluorine have? 7. Okay? And which energy level is that located? First or second? Or third? Second, because it's the second row down, right? So fluorine has these, how many protons? What's the atomic number of fluorine? 9. So it has 9 protons pulling on 9 electrons. But that electron is out there in that second energy level, which is relatively close to the nucleus. Okay? And the closer things are, the stronger the attractive force is. So when you bond that hydrogen with it, that's pretty close to the nucleus, so it tends to hold on to it stronger. Now, if you look like chlorine and bromine and all the other ones, those are way out there in those outer energy levels. So it can't hold on to that proton as tightly because of the fact that they're so much further away. And as you increase the distance, that attractive force becomes smaller. So this is why hydrofluoric acid is the only halogen that is a weak acid. All the other halogens are strong acids. Okay, so here's the deal. So if you look at HA turning into a hydrogen and an anion, that has a Ka value of 6.8 times 10 to the negative 4th. Now, let's go ahead and put that specifically as 4. Okay. Now, if I take the fluoride ion, okay, and here's the difference. If I take that fluoride ion and I put it in the presence of water, so let's say, and this, you take like sodium fluoride, okay, where you're introducing just that fluoride ion, and you put that in with water, it's going to reform the acid and the hydroxide ions. So here's the deal. So if you have hydrofluoric acid, it's going to tend to form hydronium ions and fluoride ions. And this is going to act as an acid, and you would talk about the Ka value. And this is a relatively big Ka value, okay? If you look at your numbers, this is a pretty big Ka value. So what you can look at here is that if I take the fluoride ion and put that in with water, the fluoride ion is going, oh man, I really want to make an acid, okay? Because this is how I roll, okay? This is my style, okay? I don't exist as a fluoride ion. I'm going to make an acid. So it comes up to the water and goes, hey, you know, I need one of your protons. The water goes, okay, well, I guess I really don't get to vote. Here you go, right? And then this is what's left over. You have the hydroxide ions. So in this situation, because the fluoride ion is acting as a base, then I'm going to talk about the Kb value. Now, here's the problem. I don't know what the Kb value is for the fluoride ion. It's like, ah, this sucks. I don't know. Because if you look in your chart, okay, so, now let me see. So here's the deal. So you've got a whole bunch of Ka values. And you have a small number of Kb values over here, okay? So for example, I can't look up the Kb value of a fluoride ion. I don't know what it is. It's not listed here because you're going, Burkamp, we can't solve the problem because we don't know what the Kb value is for the fluoride ion. But here's the deal. What do you know? You know that Ka, right, times Kb equals the autoionization constant of water. So if this is my Ka value for hydrofluoric acid, how can I find the Kb value for the fluoride ion? Yeah. So, Keurig, take 1.0 times 10 to the negative 14th and divide that by 6.8 times 10 to the negative 4th.
1.47 times 10 to the negative what?
1 point what?
47
Times 10 to the
negative 11.
10 to the negative 11th. Oh, okay. Now, here's the deal. So here's the ultimate big picture. Okay, so stay with me here, kids. So the Ka value for hydrofluoric acid is a relatively big Ka value. So even though it's a weak acid, stay with me here, it's a pretty strong weak acid, okay? So even though it's a weak acid, it actually tends to ionize quite a bit. So what that means is that this Kb value here is a pretty small number, because now this is where everything has to fit together. Okay, so we're going to take some random pieces of the puzzle and we're going to hopefully coalesce them into one big idea. Hydrofluoric acid is a relatively small, weak, or strong weak acid. Okay? Has a relatively large Ka value, which means it's going to have a pretty small Kb value. So what happens here is that this has to be a really, really, really small number. So what that means is that I don't make much of this, because the only way I can produce a really small Kb value is if I don't make much of this acid and this hydroxide. So here's the dichotomy. If you have a strong, weak acid, that means you have a weak, weak base. So in other words, this fluoride ion isn't going to take a lot of those protons, because I don't have to produce a very, very big, I'm producing a really, really, really small Kb value. Now, in contrast to that, if this Ka value is a really, really small number, okay, let's say this has been 6.8 times 10 to the negative 12th, okay? If this has been 6.8 times 10 to the negative 12th, that means that's a really weak, weak acid, which means this bond over here is really strong. But if you have a really, really small Ka value, then what do you know about the Kb value? Then it's going to be a relatively big number, which means you put that anion there with the water, it's going to go, oh, hello, I got to make a lot of this acid because I've got to make a big Kb value. So this is where these two go opposites of each other. So you cannot have, if you think this through, if you have a small Ka value, okay, really, really small Ka value, that means you're going to have a really, really big Kb value. So this is why, hopefully this makes sense, the weaker the acid, the stronger the conjugate base. Okay? So what that means, if you put this in terms of a dance, if you go to the dance and you're with your high school sweetheart and you know you two are destined to grow happily ever after, and it's love, true love. If you ionize at all, guess what? Your days can be going, you get back here, okay? Because if you ionize, your days can be going, whoa, 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 stop. Get back here, right? We're a couple. It's love, true love, right? So if you get away, come back here, right? Now, if you're a weak or relatively weak bond, you ionize, your day's going to be going, it's over to get something to drink. Who cares? You know, it's not that big a deal. I'll come back eventually, okay? So that's the dichotomy. So the weaker the acid, the stronger the conjugate base. The stronger the acid, the weaker the conjugate base. Now, if you do this with, wait for it, if you have a strong acid, like hydrofluoric, if you have a hydrofluoric acid and you do this, you don't have a Ka value. Guess what? Chloride ions, if you put them in water, don't do anything. If you put chloride ions, which is the conjugate base off of a weak acid, you put that in water, chloride's ions going, it's cool, right? I don't care. Might bond a little bit, really not to speak of, because by definition, that's what makes them a strong acid. Okay, so here's the last problem that we're going to work, and then I'm going to turn you loose. So let's say that we're going to have a 0.15 molar concentration of ammonia, and I want to calculate the hydroxide ion concentration and pH. So here's the problem. I want to give Morgan a 0.15 molar solution of ammonia, and I want to figure out what the hydroxide ion concentration is and the theoretical pH. So what's the first thing that you have to write down? Rice chart. Because if you don't know what the reaction is, you're dead in the water. Okay, you can't do anything. So the NH3 is going to react with water, and you can get two possible solutions. One option is you can get NH4 and hydroxide ions, okay? The other option is that you can get NH2, 1 minus, and hydroniums, okay? So these are the two things that can happen. The water takes a proton, and you get hydronium ions and NH2, 1 minus, okay? Or the water gives up a proton, it turns into NH4 and hydroxide ions. Now, in your esteemed chemistry careers, such as they are, have you ever seen NH2, 1 minus? No. You know why? Doesn't exist. It's not stable. It's like trying to find a cool freshman. They might exist, but probably not. Okay? No one's ever really seen it. So this isn't going to happen, right? So you don't have to worry about this. So that's just going to go away. Okay? So there's my reaction. Here's my rice chart. Okay? So this is 0.15. What do you think you're going to start? What do you think these initial concentrations are going to be over here? 0. Okay? Whoa, come back here. Whoa. 0, 0. And then minus x, plus x, plus x. So this is going to be 0.15 minus x, x, x. Now, because this is a base, we're going to use a Kb value. Oh, right. Kb is going to equal that NH4 concentration times my hydroxide ion concentration divided by my NH3. Now, if you look, you can find the Kb value for ammonia. Okay? So if you look, what's the Kb value for ammonia?
1.8 times 10 to the negative 5th.
So this is going to be x squared, and that's going to be 0.15, right? So here's what's going to be important. So Kira, take 1.8 times 10 to the negative fifth times 0.15, and then take the square root of all of that.
0.0051.
So give that in scientific notation.
5.20 times 10 to the negative
5.20 times 10 to the negative what?
3.
Okay. Now, here's what you have to understand. When you get X here, that's your hydroxide ion concentration. Okay? That isn't your hydronium ion concentration. This is your hydroxide ion concentration. Okay? So, if you take the negative log of this, that's going to give you your POH, right? But your pH plus your POH add up to 14. So this is the paradigm shift that you have to make. That's your hydroxide ion concentration. It's not your hydronium ion concentration. So when you take the negative log of this number, that's going to get you your POH, not your pH. So I'm going to take the negative log of that and let me know what your POH is.
2.78.
What'd you get?
2.78.
2.78? So that's my POH, so then what's my pH going to be? 14 minus that, 12, 11.22.
Yeah.
So notice that your pH is above 7. It's above 7 because the solution is basic. Okay? All right. Now, this assignment is completely out of your book. Okay, so it's 5, 20, 23, 75, 77, 78, 79, just do A, 80, just do A. Okay? All you have to do on these two problems is just the part A. And again, here's your sheet of paper, answers on the left, work on the right, unless it's like an explanation and you can write it across like that. Leave me spaces in between parts. Okay? Please.
And rice chart.
Rice charts. Be all about the rice chart.
Do we turn in the assignment?
So when you hand in that assignment, staple the yellow sheet to the top, put the bottom, put the work, and make sure, now again, I ran into this, and I'm not saying this to insult anyone, and in all these years of teaching, I've never had to do this. But make sure that you staple this correctly. Make sure that, and Kira laughs, okay? Because she was my student in the fall. The number of times I had to teach kids like how to staple, all right? I'm going to give you all, your AP students, I'm going to give you the benefit of the doubt that you know how to staple, okay? I want the edges all lined up, okay? And then put both sides of the staple through the paper, okay? It's not a difficult concept. So, but don't, I'm just telling you, don't make me give you a demonstration on how to staple, because if I do, I'm going to ridicule you unmercifully, okay? So, I'm just saying.
We're gonna upload it to YouTube.
Yeah.
Tell the whole world
Yes.
about how horrible we are at stapling.
But I swear to God, it's just gotten worse in the last like couple of years.
You can make a demo video how to staple, and you put it
Yeah.
on YouTube, you get a million views, you get famous, you get to
Yeah, become an influencer, a staple influencer.
You, where you teach chemistry, but you horribly like insult the person.
No.
Oh God.
Whoa!
I could.
That's fine.
Okay. So, quiz tomorrow. It won't be anything complex, but there's just going to be a quiz. So, we're going to quiz tomorrow, and then we'll start a lab tomorrow.
No, the only thing was, that's honest. The only thing that was, it was like.
Now I'm scared.
It was like eight.
What's your name?
So like you would count.
Morgan.
Problem.
Yep. Oh, my bad.